component analysis. We saw how to geometrically interpret the covariance. Yeah, we saw that. Let's take a look at this again. We saw that we can find a coordinate system where maximum scatter is in one direction. If we rotate our coordinate system like this, we can say, okay, the major information in the data is now contained in the x-axis, whatever x is. Because imagine if you have originally height of a person and weight, and now we rotate the coordinate system by some angle. So this is now a mixture of height and size of a person. Yeah, so it's not necessarily easy to understand what x means now, but just mathematically, the information, the largest information on the data is now encoded in the x variable. The second most important one is now in, or the less important one is now in the y-axis, in such a way that the scatter in y is minimal. Yeah? Any other rotation will lead to a larger variance in x, of course. Yeah. Now the idea of the principal component analysis is to find a transformation such that we can kind of find an ordering of this direction is the one with the most information contained, then this direction is the one with the second most, and so on. And it's done like this. So here I have some data in x and y. I compute the mean values, and first of all, I always need to center my data on the on the center of gravity of the data. This is very important, and if you don't do it, you will introduce some artificial correlation. I stress the point because there are very famous papers that forgot this. If you know, on climate physics debate, there is this so-called hockey stick paper that in the 90s from archaeological tree ring data reconstructed the global temperature over the last 2,000 years. And we saw that if you saw how's this movie called An Inconvenient Truth? So the temperature moved like this till 1900 something, and then it went like this. Yeah. So when industrialization started, the global temperature increased dramatically, and if you plot it, it looks like a hockey stick. And in this paper, they actually forgot to remove or to recenter the data. And there was a lot of criticism, and that the analysis is not significant and so on. So this got corrected, but that happened, so it's important. Anyway, so this is the data. I adjust it, but I don't plot the adjusted data. It doesn't matter. So that's the data. First of all, I compute the covariance matrix. So what I need is the variances in x and y. These are these two numbers. And then I need to have the covariance. And that's computed like the data adjusted. If you recall, the covariance is computed x minus mean x times y minus mean y, and then adding up all things. So this x minus mean value, that's what we already computed. That's our recentered data value. That's our new x value. So, and the square and the scalar product of now the new x times the new y gives us the sum overall. Okay? And then I divide by 1 over n times, over n minus 1. That's the covariance. So if I ask Mathematica here to compute the covariance matrix directly, that's exactly what I get. Yeah, so this is the covariance here. That's what we computed here. And these are the variances. Okay. This matrix contains all the information of how our data is scattering in x and y and between x and y. Yeah. So what we can do is, like with any matrix, we can compute the eigenvalues and the eigenvectors. Yeah. I do this here. These are the two eigenvalues, and these are the two eigenvectors in row notation. This is our data, and here I plot the two eigenvectors. And the eigenvectors are pointing in the direction of the primary axis of the matrix, always. Yeah? That's the first of all, and if you look at the, and they both have, of course, like eigenvectors should have, length 1, length unity. But look at the eigenvalues. The first eigenvalue is 0.3, 1.3, and the second one is very small. And that's actually the, a measure of the scatter in direction of the first and the second eigenvector. Yeah, so very small and very large. So the eigenvalues and the eigenvectors tell us in what direction the data is scattering how much. And the ellipsis that I draw here is the 95% contour. So 95% of all data points are in this thing. And you can think, of course, of the eigenvectors are showing in the major axis of this ellipsis. It's actually how it's computed. Okay, and then what we can do is we can now use, if I use the two eigenvectors as basically our new coordinate system, I can use those eigenvectors and just construct from the eigenvectors a rotation matrix that rotates my coordinate system here, just that x-axis is aligned along the first eigenvector, y-axis along the second, z-axis along the third, and so on. Yeah? That's what I'm doing here. So this is the first vector, this is the second one. And if I multiply now my data points with this rotation matrix, every xy thing is rotated into the new coordinate system. Yeah? And looks like this. If you look at the absolute values, this is from minus 1.5 to plus 1.5, and this is only 0.6 in total. Yeah? So now the most information is contained here in the x direction and less information in the y direction. And I can always, wait a second, I need to compute this first. I need, yeah. But what I can also do is I can, and that's one of the main applications of the principal component, imagine that we have not 2 dimensions but 5 or 10. Then we will get a 10 times 10 covariance matrix, 10 eigenvectors, 10 eigenvalues, and so on. And if we sort the eigenvalues in decreasing order, it's usually the case that the first few have large numbers, and then the last ones have very small numerical numbers. Which means, basically, that the scatter in the direction of the new axis is very small. In other words, they are basically sitting on this new coordinate axis with very small scatter. And if they are sitting on this axis, I don't need it, because I know, yeah, I can omit this dimension. It's not containing any information, any significant information. So I can get rid of a number of dimensions, and that's what this is used for, reducing the dimensionality of your data. In our case, we could say, okay, let's throw away our second transformed y coordinate. We don't need it anymore. We are just looking in the x. And you can do this by not using the full rotation matrix, but omitting the one with a low value. So we just take this one, and we use this smaller matrix to transform my data, and that just throws away the information. In our case, this would, from an xy set, compute a new x value only. Yeah? And that would look like this compared to the full information here. Of course, we lose information. Yeah. Now, the funny thing is, let's say we can get rid of 80% of the dimensions. So for each data point, instead of storing 10 numbers, 10 coordinates, we only need to store 2. And if we, in addition, save the full rotation matrix, we can always transform back to our original coordinate system and reconstruct our original data with some loss because we threw away some data. But this is a compression algorithm. This is data compression, what we do. We are storing a small set of numbers that's used to recreate our original data from a much smaller set. Yeah? That's another application of PCA.